All right, we're still working in chapter 5.2. This is going to now be working with variables. So we're going to do a lot of the exponent and radical, rational exponents and radicals now with variables. If it's in radical form, keep it in radical form. If it's in rational exponent form, keep it in rational exponent form. Okay, there's a couple things I'm going to show you here. Let's take a look at this first thing. Is this true? All right, so what I have here is I have the cube root of x cubed. Is that equal to x? Is that a true statement? What do you think? Yeah? Okay, let's test it with 1. So if I put 1 into that x, I get the cube root of 1 cubed. Is that equal to 1? Okay, on this side, the cube root of 1 cubed would be the cube root of 1. Is that equal to 1? And 1 is equal to 1. Sure is. All right, good. Let's go down and let's take a look if I put a negative 1 in there. So I would have the cube root of a negative 1 cubed. Is that equal to a negative 1? That's right. So the cube root of a negative 1, is that equal to a negative 1? Cube root of a negative 1 is negative 1. It's equal to negative 1. Yeah, that's true. And for situations where I have an odd index, where the index is odd, that's always going to be true. Okay? Let's look at another case. We're moving over now to this case where I have the square root, and I put a square there. We don't really have to put a 2 in the index, but I'm just to remind us that we are using an index of 2 of x to the 4th. Is that equal to x squared? Now, we would think so using rational exponents. Remember, by rational exponents, that would be x to the 4 halves. That would be equal to x squared. So is that true? Let's take a look. So I'm going to put 1 in there. So I've got the square root of x, sorry, I don't want x, I want 1, to the 4th power. Is that the same thing as 1 squared? To the square root of 1, is that the same thing as 1 squared? The square root of 1 is 1. 1 squared is 1. Yeah, that's true. So it works for 1. Let's test if I put a negative 1 in there. Okay, so remember what that was. That said the 4th root. We said that the square root of x to the 4th, is that equal to x squared? So using a negative 1, that would be the square root of a negative 1 to the 4th. Is that the same thing as a negative 1 squared? Okay, so negative 1 to the 4th is going to be 1. And negative 1 squared is 1. So the square root of 1 is 1 equal to 1. Yeah. Looks good. Let's do another test case. Okay, now I have x squared under a radical and to the square root. So rational exponent form. Looks right to me. Let's test it out. All right, so I'm going to test 1. So I've got 2, the square root of 1 squared, and putting 1 in for the x. It's equal to 1. So I have the square root of 1 squared. Is that true? 1 equal to 1. Yeah, it's true. Okay, so far so good. Let's test the negative 1. Remember what we originally had? Okay, so let's put a negative 1 in for both x's. Okay, so now I'm going to square a negative 1. It's not true.
But it's plus minus 1.
So, remember, these are not, this is not a solve. This is a simplify. Okay, so what we see here is that we have generated a case where I'm taking the square root and it's not going to be equal to a -1. And that's because I'm squaring something under the square root. And let me try to explain how we're going to deal with this situation. Okay, first, if I have an odd index, whether it be the cube root of x cubed or the cube root of x to the 6th, this will be x to the 1st, this will be x squared. I don't have any issue at all. That works fine. In this other case over here, I had a situation where, for example, I had a square root of x to the 4th, or I could even say a square root of x to the 8th. And what I get when I would take this out of there, if I would get x squared or x to the 4th, I have an even index. The index is even. And when I simplify what's under the square root, I get an even exponent. The fact that these exponents are even, if I would put a negative number in for x, the squaring, or the 4th power, takes that negative away. So the problem is going to occur when I do have an even index, but I don't worry about it when I simplify, as long as what's coming out has an even exponent on it, in this case a 2 or a 4, I don't have to worry about it. That's also okay. The problem occurs that when I'm taking an even index and when I simplify it, it comes out, and the power on what comes out is going to be odd. If I'm using a negative number, it's going to be negative on the outside also. So that's my case that I need to add something to what we've done before. And how you deal with that is you simply add an absolute value. So on the case where I have even indexes, and when I simplify what's under the radical, and it comes out to have an even power, what I do is I simply add an absolute value there to make sure that I take care of any negative. Okay? So let's review how we're going to deal with that situation. It only occurs on radicals where I have even indexes. When I simplify the radical for a variable, it's going to be a variable, when the variable comes out and it has an odd power coming out of the radical, then I need to use absolute values to take care of any negative. Okay, let's work some examples. So what you have to have here is you cannot have any perfect powers of this index underneath there. So I cannot have any perfect cubes underneath the radical for letter A. So I'm going to look at 64 and I'm going to decide how can I break that up into any perfect cubes. As it turns out, 64 itself is a perfect cube. It's 4 cubed. And I can look at the y to the 6th as y cubed times y cubed. It's a cube root, so I don't have to worry about any absolute values. So the 4 cubed comes out as a 4. The y cubed comes out as a y. This y cubed comes out as a y. So my answer is going to be 4y squared. There's nothing left underneath the radical. Everything came out. Now, a lot of you aren't going to be messing with breaking this y to the 6th up. You're simply going to think of it as y to the 6th divided by 3. Oh, that comes out as a y squared. Breaking them up into 2 separate y cubes, you could do that, but you may decide not to. Let's move down to the other one that's similar. I have the cube root of 27, d to the 12th. So I'm going to take a look at my index to see if I need to worry about absolute values. It's an odd, so no, I do not on this case. And I'm going to think to myself, I need to get all perfect cubes of 27 out of there. Well, 27 itself is a perfect cube. And then I have d to the 12th. So what's going to come out is the cube root of 3 cubed comes out as a 3. And this d to the 12th would come out as d to the 4th. 12 divided by the index is 4. So everything comes out of there. That would be 3d to the 4th. Let's move over to the ones that have fractions underneath the radical. And the first thing I'm going to do is say, well, maybe I can simplify this by dividing my denominator into my numerator. But y to the 8th will not divide into x to the 4th, so I'm stuck with this like it is. So the next bet there is just to break it up into its numerator and its denominator. They're both 4th roots. Okay, so for the denominator, now I do have to think about my index. It's even. So for the denominator, this is going to come out as a y squared. Okay, but because my power is an even power, I don't have to use absolute values for my denominator. It's simply going to be y squared. Okay, let's look at the top. I have x to the 4th power, and I'm taking that to the 4th root. That's going to come out as an x. But that power on that x is a first power. So that's one of the situations where a negative will be a problem. So what I have to do is I put that x to the first power in absolute value signs. Okay, let's go down to the next one. Unfortunately, some of these examples are real similar to each other, but so let's break this up. I can't divide y to the 16th into x to the 4th, so I'm going to have the 4th root of x to the 4th, and in my denominator, I have the 4th root of y to the 16th. Okay, they're both even roots. I may have to use absolute value. For the denominator, I'm going to have y to the 4th, 16 divided by 4. The exponent is even once it comes out, so I don't have to worry about absolute values. For my numerator, I have x coming out, x to the 4th, that would come out as x. X to the 4 divided by 4 is a power. And because the power on that x is 1, it's an odd, I do have to have absolute value signs there. Okay, let's move to a different kind of example. Now we are simplifying stuff underneath a radical. And I need to ask myself, okay, first thing, it's an odd index, so I'm not thinking anything about absolute values. All I'm doing is trying to get all perfect roots, powers of 5 out. So anything that is a 5th power, a 10th power, a 15th power needs to come out. Okay, so the number 4, there's no way that number is going to be a 5th power of anything. It's going to have to stay underneath the radical. Now, a to the 8th, I could break that up or think of it as a to the 5th times a to the 8th, where a to the 5th will come out as an a. For the b to the 14th, I could think of that as b to the 10th times b to the 4th, where b to the 10th would come out as b squared, 10 divided by the 5, leaving me with a b to the 4th still underneath the radical. Okay, so the b to the 4th stays under the radical along with the a cubed. And the last letter, c to the 5th power, will come out. That would be c to the 5th, and it will come out as a c because that would be the same as 5 divided by 5 would be the power on the c. So it comes completely out. Okay, let's look at the next example. Now this is a little bit different kind of an example. I have a radical in the denominator, and we know we cannot have that. So let's go ahead and simplify what I can do with that radical to see what I have to do with my next step. So I have y to the 8th. First, it's an odd index. There's no absolute values coming into play here. So I have an odd index, and I'm going to break y to the 8th into y to the 6th times y squared, where I know that y to the 6th power is going to come out as y squared. Okay, so when I do that, I'm going to end up over here with y squared times the cube root of y squared, because this y squared couldn't come out of the radical. The problem is I can't have a radical in the denominator. So somehow I need to get this y squared to become a cube, because, and I left my little cubes off here. Okay, so how can I make this, what's under the radical y squared, actually become a y cubed? Well, how about if I multiply it by the cube root of y? That, because they both have cube roots, they can combine under one radical, so y squared times y would give me y cubed. Since I multiplied the denominator by the cube root of y, I have to multiply the numerator by the same thing. Essentially, I'm multiplying by 1. So when I'm all done with that, I'm going to get x times the cube root of y all over my y squared. And now I do have y cubed underneath the radical sign, so that y cubed comes out as y, which will multiply by y squared, giving me y cubed. Okay, let's go on to another example. Okay, here, and this is some of these in the book are a little too simple. This is simply rational exponents. I'm going to keep it in rational exponents. I'm not going to switch it to radical form. So I've got two numbers, a 14 and a 2, so let's look at them. That's going to just give me a 7. I have an x, and one's a numerator, one's a denominator, so I'll subtract the exponents. The largest exponent is in the numerator, so that'd be 1 minus 3/4. So that's going to give me x to the 1/4. Let's move on to the y. I've got y to the 1/3. There are no other y's in the problem, so y to the 1/3 stays as y to the 1/3. Then I have z to the -6 down in the denominator. No negative exponents, so the way to get rid of this negative exponent on the z is it goes up to the numerator position, giving me z to the 6th. Okay? All right, I'm going to have to jump ahead here. What we have down here at the bottom are some adding and subtracting. This is a little different. We don't treat variables any different than numbers. What we have to have is if we want to add these two radicals together, they have to have the same index and they have to have the same radicals completely. So since I have 5 times the square root of y, and over here I have another square root of y, but it's 6 times the square root of y, the 5 and the 6 can simply add, giving me 11 times the square root of y, just like we did with numbers. There's sometimes I could have a problem where my radicals don't actually match, so I can't combine them. But like with numbers, if I can simplify them and make them look the same, then I can combine them. And that's the case here. I have this z to the 5th. So if I can make that z to the 5th z cubed times z squared, well, the z cubed comes out as a z. It leaves me with z squared underneath the radical. And what I end up with is 12z times the cube root of 2z squared. All right, let's look at the other piece. 54z squared. Well, 54 is 27 times 2. 27 is the cube, 3 cubed, so that comes out as a 3. So I can simplify that into 3z times the cube root of 2z squared. Now my radicals are the same. So it's simply 12z minus 3z. That's 9z times the cube root of 2z squared.